Okay. Okay, welcome to the second part of this lesson 2 for the module Maximum Entropy Network Ensemble. In this second part, we will cover random graph and canonical ensemble with constraint given by the expected degree sequence. So let's start with random graph. Random graph have been proposed by Erdős and Rényi in the 60s, and this has been a very important leap in graph theory because they were the first that had this wonderful idea to introduce a probability measure in the space of graphs. And in fact, they introduced the first well-known graph ensemble or network ensemble. And this random graph ensemble comes in two types. So we have the G and L ensemble, which are the ensemble of all the graph with exactly n nodes and L links. So you have a set of nodes and you draw L links among these nodes in a random way. Or you have a GNP ensemble in which you have graph with n nodes in which each pair of node is connected with probability p. And what you are doing in this GNP ensemble is actually fixing the expected number of links, because if between each pair of link you have a link with probability p, then in the network you will have p and choose 2 expected number of links. And these ensembles are therefore one the microcanonical ensemble and the other the canonical ensemble, in which you constrain the number of links, as an hard constraint and as a soft constraint. And we are particularly interested in the sparse regime, so in the regime in which the average degree is constant while the network size can be growing, can be going to infinity. So if you have a graph in which the average degree is, you name it, 10, 100, and the network size can be as large as you want. And in these graphs, the degree distribution is power law. Is Poisson. Sorry. So it's not power law. So this is, and it's not heterogeneous. So this is why these graphs are very important, but they are not particularly realistic, because in a number of realistic situations, you have instead that the degree of the node can fluctuate very widely. Instead, in this graph, the distribution is quite localized around the mean. So exactly, so this random graph, there are microcanonical ensemble in which you fix the total number of links, or canonical ensemble in which you fix the expected total number of links. So we have seen that the canonical ensemble, in this case the GNP ensemble, will have an exponential Gibbs measure, which is in fact a probability assigned to each graph, and here we identify each graph with the adjacency matrix. And the probability of each graph will be, according to this general theory, 1 over the partition function e to the number, sum over the number of constraints, but the number of constraints is 1, then the Lagrangian multiplier, and then the observable, which is the total number of links here. So this is the probability of a graph with adjacency matrix A in the random graph ensemble, GNP ensemble. So this probability can be also written as in this form. So here you see that this probability factorize in term that depends only on the link ij. And in fact, it can be expressed as probability of the network is a probability of observing a network with adjacency matrix Aij, where each link between node I and j is drawn independently with the probability which is given by this marginal probability, which is Pij. So practically you have the network, and for each pair of nodes, you draw a link with a probability P, which is independent on the existence of other links in the network. And in this Pij in particular, for the random graph, is the same for each link and is exactly equal to P. And this is why we call this ensemble GNP ensemble. And this P is, as can be expressed in terms of the Lagrangian multiplier lambda by using this expression. Okay. And by using this P and this probability, you can find out that this probability of a graph A is just given by this expression P multiplied to the power L, where L is the number of links in the network that can oscillate, can be is a random variable. And then you have 1 minus P multiplied by to the power that indicated by this expression, which indicates the number of missing possible links among a pair of nodes. So let's derive this expression. So what we want to do is to start calculating this partition function, which is, as you remember, the sum over the adjacency matrix of this exponential. No? Here we have e to the minus lambda, the total number of links. So what do we mean by that? So when we sum over the adjacency matrix, all the graph, we mean that we have a symmetric matrix A. So we mean that for each element of this upper triangular matrix Aij, we sum over all possible values, so 0 and 1. So for A12, we sum 0 and 1, A13, 0, 1, an minus 1, and 0, 1. And here, this quantity we express as the probability, the exponential of e to the minus lambda sum of Ij, we express as product of I less than j of e to the minus lambda Ij. Then we practically attribute to each sum the corresponding factor. So you see that each sum can be conducted independently and has the same value, because this element of the adjacency matrix is a summation index here. So here I can write that this partition function is the product of I less than j of this sum, the sum over a generic element of the adjacency matrix Ij over values 0 and 1 of e to the minus lambda Aij. So here, if the adjacency matrix is 0, I get 1. If it's 1, I get e to the minus lambda. These are all the same for every I less than j, and I get this expression. Okay, so there is nothing very special about this calculation, just one need to get a little bit trained on the fact that when you sum over the adjacency matrix, you really sum over all these elements of the adjacency matrix. So similarly, we can calculate this marginal, the probability that I is connected to j, which is the sum over the adjacency matrix of Aij P of the probability of that graph, which is nothing else as the Gibbs measure. So we put 1 over z e to the minus lambda sum over r less than s a r s. So we change the name of the index here. It's not anymore Ij, because Ij is this one, this particular link that we want to see what is the probability to observe it. And here, so we have these and all the other links. So again, we explicitly write the sum over all the matrix elements. Here, exponential of the sum we write as a product of different exponential. Aij remains unchanged. And now here, when we distribute term by term to each sum, you know, every sum is the same, except when I sum over the matrix element ij, in which I have this factor aij, and then I have e to the minus lambda aij. Okay, but all the other are the same and the same as before. So here, if I focus on this term, when aij is 0, this gives a 0 contribution. So I just need to consider when aij is equal to 1, and I have e to the minus lambda. And then all the other terms are, you know, all this product of r less than s, but different from ij, of these sums that are all the same and are all equal to 1 plus e to the minus lambda. Okay, so here I have to write 1 plus e to the minus lambda to a power n choose 2 minus 1, because I don't have to consider ij. And when I insert this formula for z, there is a simplification and I get the expression for b. So p, and this expression is independent on ij, so the probability that I observe a link between node I and j is independent on ij, is equal to p, and is related to lambda by this expression. Okay, very good. So this is a little bit the basic. So it's important that you spend some time here, because then we will do similar calculation later on. So if I want to know what is the expression of the expected number of links, okay, so in this ensemble, I sum over the link over and sum over the adjacent, and do the average of the number of links over the distribution of the network. I can change the order of summation, and here I get the marginal Pij, and then I get this, since this marginal is the same for every I and j, I get P n choose 2. And therefore, really, I found that, you know, this relation between the probability of the G and P ensemble, of the probability of observing a link, and the expected number of total number of links in the whole network, which is given by this relation. Okay, so really here we show in some sense that the G and P ensemble is equivalent to the canonical ensemble, in which I fix the total expected number of links, expected number of total all the links. So now I want to show that this probability really factorize for each link. So practically I have this expression where I remember the expression for z that we just calculated and the expression of p that we just calculated. And by using this expression, I can rewrite p of a in this way. Okay, so practically I have that the network can be thought as the drawing of dependent drawing of links between each pair of nodes with probability p. So if each pair of nodes is connected with probability p, and the network is the result of this independent drawing of links. I can also write the log likelihood of corresponding to this model, and it has this model, and it has this expression here. So here, maybe I want to go quickly over this slide. It's just a summary of what we have discussed in length before. So if you use maximum likelihood, then you get exactly that, you know, the the P that you have to choose is given by the density of link that you observe. So here P is equal to the density of link that you observe in a given data set. So if you have a given data set and you want to know the best approximation with the GNP model, you have to choose P equal to the density of links observed in the data set. It's just as simple as that. So in the sparse regime, we have that this expected number of links should scale like the number of nodes where the average degree is constant. And therefore, if we substitute this, we find that P is equal to the average number of link divided n-1. And if n is very big, you have this famous expression, which is the average number of links over n. So this probability of observing a link in a sparse network is not constant with n, but is vanishing with n, okay? And is vanishing as 1 over n. In this ensemble, you might want to consider the probability that a node has degree k, and this is given by a binomial distribution with average p. And if the network limit is large, then this binomial distribution converges to a Poisson. And for this reason, this network of the GNP ensemble in the sparse regime, so when the average degree is constant, are also called Poisson networks. So, so you have this expression for the entropy, given this expression for the probability of the graph, meaning that the graph is the result of this independent drawing of links for each, connecting each pair of node potentially. And interesting, when you insert this expression in the expression for the entropy, you find a kind of expected result. So the entropy is like the entropy of a Bernoulli trial, but not just one, but one for each possible link in the network. And if you substitute to P the expression in terms of the average degree and n, in order to see how it scales with n, you find this expression below. Okay, so this is a quite interesting expression, because then it's very interesting to study the large network limit. So what is the scaling of the entropy with the number of nodes in the graph when the network is very large? And here we find something that you don't find typically in statistical mechanics, which is typical for a graph. And that is the entropy of this ensemble is not extensive, in the sense that for the random graph, there is a term that is the leading term in this sparse regime, which goes like n log n. You see, here is, you have the practically, this expression means the number of links logarithm of twice the number of links, and it goes like n log n. So it's not linear in n, but is going faster than that. But interesting, there is a sublinear term which is extensive, and then there are, you know, also other and other less negligible term. So really, why do I stress that there is this extensive term, which is not the leading one? Because when we will see, when we will change the degree distribution by having a given network with given degree sequence, this first part will be unchanged, so will be independent on the degree distribution, the same as in the random graph. And this extensive part instead will carry information about the degree distribution. So practically you can, in some sense, subtract this part which only carries the information about the expected number of links, and then this extensive part gives more detail about the network that you are considering. But this is an indication that in networks there is a problem of, it's not very easy to add networks. If you have a network, two networks, if you putting them in some sense in contact, there can be a lot of links that can be established between them. So this is in some sense a bit of the reason why the entropy is not just additive. Okay. So yeah, if we want to prove that, it's just you start with this expression in which instead of p you have k average n, which is p log p 1 minus p logarithm of 1 minus p, and instead you put k average over n, and you just expand for n going to infinity, and you get this expression. Okay, so it's just an expansion, a simple expansion. So we have the microcanonical ensemble now that we want to consider. So the GNL ensemble, in which is the random graph in which we have n nodes, but exactly L links. So the links are not allowed to fluctuate, but we have exactly, our desired number of links. And this probability of this network is uniform over all the network which have exactly L links. And this partition function is nothing else than the number of graphs that I can construct with L links. Okay, and this, since practically I have complete freedom of where to put the links, so I can put it between any I and j. So in an adjacency matrix that of a simple network, I have all the elements, the upper triangular elements, which I can put a link in, and these are n minus 1 over 2. And then and there I can, in each of these I can put or not put a link. So I have this, the total number of graphs that I can construct with L links is n minus 1 over 2 choose L. So clearly the entropy is the logarithm of this number, is the logarithm of this number, simply like that. And what you can show is that if you write L as in terms of the average degree and n, and you expand this expression for using Stirling expression for factorial, and using the logarithm and things like that, you can find that sigma and s are the same if you neglect higher order terms. So this means that the GNP and the GNL ensemble are asymptotically equivalent. Okay, so if you want to know a little bit more about this network, if you want to be curious, for instance, about the clustering coefficient, it's interesting to observe that if you have a network and a node I, which has degree ki, the average clustering coefficient is independent on I and is the average degree over n. Therefore, this is vanishing. So this means that this graph have very few loop, have very few triangle, and in reality, if you want, you can measure the expected number of triangle in this graph, and you find that is a fixed number also in the large n limit. So if you go in a network that is you go for n going to infinity, you find always a fixed number of expected number of triangle. That means that practically this number is completely negligible. Okay, so these networks are locally tree-like, so they don't have many triangle or short loops, but they might have very long loops, loops of size logarithm of n. This network, however, have a diameter which is logarithm of n. So they are in some sense, they have this property that is the diameter is rather small compared to lattices, for instance, and therefore if you want to define an Hausdorff dimension, you need to put this Hausdorff dimension to infinity. So, okay, so this concludes the part on the random graph, and then now we can consider the ensemble, in which instead we fix the degree sequence in average. So of course you can think that in this way you can continue as you want. So now you fix the degree sequence, then you can ideally you can fix the community, you can fix also, maybe you want to fix the triangle if you want, and ideally this is what you want to do in some sense, so to refine more and more your model in order to approximate your real network as much as you want. Then technically you can run into quite significant problems, in particular when the constraint is non-linear. So if the constraint is linear, like for instance, the degree is linear in the adjacency matrix, is the sum of the row of the adjacency matrix, then this is, as is technicality, but is doable. But when you want to constrain, for instance, the number of triangle or the number of wedge, you can find phase transition, so very anomalous behavior that we might I can describe to you a model which display this kind of behavior, but it's really becomes much more complicated to treat, in particular analytically. So let's start with the first important specification and generalization of the random graph, in which we take the degree sequence as constraint. So here again, we can have a microcanonical ensemble or a canonical ensemble. In a microcanonical ensemble, you practically define for each node what is their degree, and then you match these stubs, okay, in order to form a simple graph. You want to that the graph is simple, but and this is called the configuration model, and is the microcanonical ensemble in which you have a given degree sequence. Another approach is the one in which you have a canonical ensemble, so a Gibbs measure, in which practically you draw the network according to the Gibbs measure, and these are called exponential random graph. Okay, and in particular, when the constraint is the expected degree sequence, then you will find always that you can draw each link independently on the other link, but not with the same probability Pij, but Pij will depend on I and j, the value on I and j, so will be heterogeneous. Some nodes will are more likely to be connected than others. So in the canonical ensemble, so we fix the expected degree of each node. So we consider a set of n constraints, because for each node we fix what we would like what is the degree that we would like to see in average over the ensemble. And so we know, because of the general approach, that this canonical ensemble will have a Gibbs measure. So the probability of the graph identified with the adjacency matrix is given by this Gibbs measure. Then we have capital P equal to n. So we have the sum over all the constraint of the Lagrangian multiplier associated to each constraint, so to each node I, essentially, of the constraint, and the constraint is nothing else than the degree of the node, so the sum of the element in the ith row of the adjacency matrix. Okay, so this will be our Gibbs measure for the ensemble that we want to consider. And now we want to show that the Hamiltonian, you remember this term that we have at the exponential, that is sum over I between 1 and n of lambda n, and the degree expressed in terms of the adjacency matrix, can be also expressed in this way, like the sum over I less than j of lambda I plus lambda j aij. So we sum only, while this left-hand side depends on all ij, upper triangular, lower triangular element of the matrix. Here we consider only one side of the matrix. So every element of the matrix is considered, every element associated with a given link is considered only once. And the partition, so this is very convenient to do the calculation because we have to sum over this element only once. And the partition function is instead given by this expression. So let's show this. So we have this given measure. You remember the Hamiltonian is what is here in the exponential. So we want to show that this Hamiltonian has this shape ai sum over I less than j aij multiply lambda I plus lambda j. So we start with the definition coming from this expression here, sum of I equal to 1 of n of lambda I sum over all the j from 1 to n of aij. So now this is practically the sum over I and j of lambda I aij, okay, where these indices are summation indices, so I can call it as I want. So I write this as 1 over 2 as the sum of two terms that have the same value, one in which I call the first the indices in which I sum I and j, and the other in which I call the indices in the opposite way. So these two sums are exactly the same, and each equal to this quantity before. So I put 1/2 in front, and then I use this trick because now I can use the fact that the adjacency matrix is symmetric. So this is aij multiply lambda I plus lambda j, and now I have aij is symmetric. Also, this term inside the bracket is symmetric. So I can just write this as summation over I less than j of this term. And I prove what I wanted to prove. So it's just a little manipulation to have this expression. So now I can write the Gibbs measure with this new expression for the Hamiltonian. And I want to calculate the partition function, which will be fixed by the normalization of this Gibbs measure. So given by the sum over all the adjacency matrix of E to the minus the Hamiltonian. So again, here I did not put all the detail of this derivation, but when I sum over the adjacency matrix, I sum over all the upper triangular element of the adjacency matrix, which are independent, and some of each one can take value 0 or 1. And then I have this term, which can be also factorized as term dependent only on I and j. Then this allows me to write this thing as product on I less than j of summations that are all the same, and they are the summation over the generic matrix element ij that can take value 0 and 1 of what? E to the minus aij, and now is multiplied by lambda I plus lambda j. This is very similar to the random graph calculation, but now we need to take care that the Lagrangian multiplier is associated, is different from node I and node j. And we have 1 for each degree. So this leads us, when you sum over value, when you have value aij equal to 0, we have 1. When aij is equal to 1, we have e to the minus lambda I plus lambda j. And this is expression for the partition function now. So good. So now we want to find the marginal, so the probability that I connects to j. This is the sum over all the adjacency matrix of the elements of the adjacency matrix ij multiplied by the probability of the graph. And we want to show that this probability that I connects to j has this form, which is an interesting form, which depends on I and j in a non-trivial way. So it cannot, is not just depending on I and j independently as 2 factor, but as this kind of logistic expression. And then given that if we derive this marginal Poj in this way, we want to show that the expected degree, the constraint, will be practically that the expected degree should be equal to the sum of Pij over all j different from I. Okay, here there is a mistake, sorry, in this slide. So this should be, again, here a sum over j also of this right-hand side, sorry. Yes, so we have the partition function we calculated before, and when you consider and here we express in terms of rs instead of ij, not to confuse with this ij of the marginal. And here we calculate the marginal, so we put aij and then the Gibbs measure expressed in terms of R and S, and this is R and S. So again, here you do the same calculation similar to the one that we have done for the random graph. So you have to sum over all the elements of the adjacency matrix. And when you sum over the element R less than S but different from ij, you have just the sum over these terms. When you sum over I and j, you just have e to the minus lambda I minus lambda j. And then when you insert the expression of z, you find the expression for the marginal. It's just, we can go a little bit over if you want later on, or if you need it, but if you try to do step by step as we have done for the random graph, it should be immediate. So then the expected degree for each node is nothing else than the probability of the degree of each node. So here we can change the order in which we do this sum, and we find that the expected degree is nothing else than the sum of the probability that I connects to j, sum over all j in the network. And we have this expression. Okay, so here I notice one thing. In general, you don't want to sum over j equal to I. So here, strictly speaking, you should put j different from I. What happens is then, if in this ensemble, if the probability ij is each one is very small, so yes, so it is 1 over n. So if you add also the term including I, you will find that this is a negligible term. But in general, you should put j different from I here. Okay, so the probability, again, you can show factorize into term depending on each link independently. So again, this network can be thought as the draw of independent links, each one occurring with probability Pij. And so this simplify a lot if you want to generate these networks. And you can consider the entropy of this ensemble, and you just use the Gibbs measure, and we have seen how to derive the entropy of a canonical network ensemble in general in part 1. So this will be sum over I between 1 and n of the Lagrangian multiplier of node I, the value, the expected degree, then our constraint, plus the logarithm of the partition function, which you can also write explicitly in this way. So the entropy, again, can be expressed also alternatively using the expression of POA in terms of the marginal. And again, here you see it is practically the entropy associated to n choose 2 draw of links, each one as drawn as a Bernoulli variable with probability ij. So so an important thing is that this entropy here will depend on Pij. So, and Pij will depends on the Lagrangian multiplier lambda I and lambda j. So ultimately, this entropy will depend on the degree distribution of the network, not only on the average degree. So if you have 2 different ensembles, one in which you have the same number of links, but the degree distribution, the expected degree distribution and sequence is different, then the entropy of the ensemble will also be different. Okay, and in particular, this extensive part of the entropy will be different, and this is quite interesting, and we will discuss more in detail in the next class, because this indicates that yes, really this entropy capture some important property that are associated with different degree distribution, not just the average degree, but really the nature of the distribution itself. So finally, you can play the game we have been playing all over, and rephrase this maximum entropy approach in terms of maximizing the log likelihood. So if you have a graph, that you observe a graph which has a given degree sequence, you want to know the best model that approximate this graph, the best model with expected degree sequence that approximates this graph. You define the log likelihood, which is minus the logarithm of the probability of observing that graph with a given with a set of given Lagrangian multiplier which you don't know, and you express this in this way. And then or alternatively, you can express also the log likelihood using directly the marginal, and then you express it in this way directly with the marginal in this way. So here, if you want to find the best Lagrangian multiplier, the best model which describe your data set, you maximize the log likelihood. And again, here, it's no surprise, you find that when you derive that practically you will obtain an ensemble, which is the ensemble with given expected degree sequence, in which the constraint, so for each node, you will have an expected degree, which is exactly equal to the degree that you observe in your specific data set. So this is a way that tells you how you can randomize a network in some sense also, right? So you have a model that best approximate your real network. So you can also use this model to randomize the network that you have. You know, your network might have some additional feature, but you can approximate by this random network with this constraint. So finally, we conclude this second part of the class, and then we can discuss later on about more detail about that. So we finish this discussion of this part by describing how to generate network in the canonical ensemble. And then there are essentially two methods. The one that is mostly used is this one. So practically you have a given expected degree sequence, which is either given by the degree sequence of a network that you are observing, or a degree sequence that comes from a given distribution that you want to model, a Poisson or a scale-free distribution. And given this degree sequence, you calculate the Lagrangian multiplier. So you need to find numerically, in order this equation should be solved numerically. You should find the Lagrangian multiplier lambda I, which satisfy this constraint for every I between 1 and n. Okay, so this you can do, for instance, iteratively. It cannot be done analytically, but numerically, the convergence typically doesn't cause much problem. And then once you have the Lagrangian multiplier, then for each link ij, for each pair of node ij, you draw a link, you put aij equal to 1 with probability pij, otherwise you put aij equal to 0. Okay, so you don't have a link. And so in this way you generate one instance of network ensemble that you want to do. Okay, and you can, and since yeah, so this is, you have to look at all the pair of nodes. So you have to go to and choose 2 choice of drawing a link. But once you calculate the Lagrangian multiplier, you can draw independent network just by repeating this last step independently. An alternative way is to use the metropolis hasting. This is much less used as I gather, as I expect, but you can start with a network of n nodes, calculate the Lagrangian multiplier as in the previous algorithm, And then you can iterate this metropolis hashing algorithm until convergence of the observable. So you pick a random pair of nodes and you can flip, in some sense, a link with this probability, which is given by the minimum between 1 and the ratio between the probability of the flipped the new proposal for the adjacency matrix and the probability of the actual graph you are starting with. So this concludes the second part of today's second lesson. So we have applied, in some sense, this general framework of network ensemble to some specific cases. And in particular, we have covered random graph, finding that random graph, satisfy only one global constraint, and so they are equivalent ensemble, but they can be, microcanonical and canonical ensemble corresponding to the GNL ensemble and then GNP ensemble. And then we have started to investigate what happens when we further refine our constraint and we impose as constraint a given expected degree sequence. So in the next lesson, the idea will be to introduce degree correlations in network. And then, because this will allow us to define what is a natural cutoff, which is quite an interesting concept. And this will be used to discuss the micro and the canonical and the microcanonical ensemble and their non-equivalence. Okay, so here we will have different choice. Maybe we can discuss later on what you would like to do, if you would like to do to focus more on the theoretical aspect, or if you would like more of a kind of insight about network modeling and analysis with this degree correlation. Okay, so this finished this lesson for today, and we can start the discussion when I stop the recording.